Welcome, everyone. Welcome to another exciting Friday webinar with our graduate students. And today it's all about going far into the universe, which so many of us love. So this is really exciting. My name is Christian Sass, by the way. I'm the astronomer in charge, and I run these webinars. And today I'm very excited to introduce to you our speaker, Delaney Dunne. And Delaney is a fellow Canadian. She comes from the Prince Edward Islands. I hope I got that one correct. And she went to McGill, of course, nearby, all on the East Coast. And then she flew all the way to the West Coast to Caltech, where it's a very hot day. And they're also on very hot topics. So Delaney, welcome. And we're really excited to hear about your topic today.
Thanks so much. Just share. All right, is that set up?
Perfect. You just have to tell me when you want to launch your polls, and we're all set. Thank you.
All right. So I guess we'll just get started. So as I said, my name is Delaney Dunne. I'm a PhD student at Caltech, and I work on an experiment called COMAP, which does something that's kind of niche even for astronomy. It's called line intensity mapping. And so there's a lot to break down about that. We're going to take it slowly. We're going to start with the acronym itself. COMAP is my project's name, and that stands for CO, or carbon monoxide, mapping array project. And we're going to get into why all of these various components of the name are important. So the talk we're going to start with, I flipped these. We're actually going to start with how a star is born, which is the CO component. Why carbon monoxide? What's going on with that? And then we are going to start about talking about mapping the universe through time and through space in all three dimensions, all four dimensions almost. And then I'm going to introduce line intensity mapping and the project specifically. So let's get going. So first step, how a star is born. This is something that maybe some of you are somewhat more familiar with, maybe some of you aren't. But in order to get into it, we're actually going to start sort of earlier on in the universe. So when we think of the universe, most of us think of, galaxies and stars and planets and that sort of thing, but that's actually not true statistically. Of the regular baryonic matter in the universe, most of it is just hydrogen gas. And so this is a simulation of some of that hydrogen gas in different phases. Hydrogen actually comes in sort of three flavors that we're going to be talking about today. It's just a very simple molecule. It's just a nucleus and a single electron. And in the universe, you can find it like that. This is that neutral hydrogen in the middle. But you can also find it ionized, where the electron has been stripped off. And you can find it in a molecule, where two hydrogen atoms have combined forces to make a single molecule. And these are arranged in order from hottest gas to coldest gas, because it takes a lot of energy to strip off that electron and have just a hydrogen ion. And then it is really easy for very cold hydrogen to group up into these molecules. And in the universe, where we don't have sort of the gravity we think of on Earth keeping things clumped together, we just have self-gravity, molecules attracting each other. We actually tend to see molecular hydrogen in very dense regions and ionized hydrogen in very diffuse regions. So I think we can kick it off with our first hydrogen poll, if we want to do that.
1 second. Just give me a sec. I'll launch it. Where are we? The polls. Okay, the hydrogen one. Let me just see which one it is. 1 second. Oh, yeah, the hydrogen gas one, right? Here we go. Yes.
As we are voting on this, I'm going to show a brief simulation of how these sort of hydrogen types play with each other in the universe itself. This was made by the Fire Group, which is hosted at Caltech. And this is the simulation of a galaxy forming from sort of very early on in the universe until very recently. And the magenta is the molecular gas, and that's what we're going to be talking about today, the densest, coldest gas. And you can see that most of the universe, for most of the universe's history, is very hot ionized gas, and then it's sort of funneling this cooler ionized gas onto this forming galaxy in the middle. And it's going to take a minute or two for it to actually look like a real galaxy, like we're used to seeing, because it does take a while for that gas to cool and condense into something that looks like a galaxy. So all these little outbursts are things like supernovae going off, or things like black hole jets. You can see other galaxies are coming in and merging with the original galaxy. And eventually, after this one last outburst, we're going to get sort of a reasonable looking spiral galaxy.
And just quick
And
question,
that,
Delaney, and
yeah,
you think that still would be very true with the recent findings from the JWST, where it seems that a lot of the galaxies were formed much earlier than we thought. It would still be true. You think so?
I think so. Yeah. So what we are seeing with JWST, there's a couple caveats to it. First of all, that's so far away that we are only seeing sort of the very brightest and most extreme objects in the very distant JWST samples. So it's plausible that these are just sort of outliers. We don't really have a good look at the whole population of galaxies. And I'm actually going to be mostly talking about a method for looking at the whole population of galaxies. And then the other thing I will say is hydrogen we understand okay-ish. What we don't understand quite as well is all of the other chemistry that happens in galaxies. And so I think most likely there will be some tweak to our understanding of the chemistry to explain those galaxies, but not positive. We could sort of disrupt everything. We're not sure yet.
Do you want to comment on the poll result?
Yeah, I'm seeing it now. So it looks like most people are actually fans of ionized hydrogen, the very, very hot, very energetic hydrogen, which is cool. Hopefully, we will change your mind and get you onto molecular hydrogen by the end of this talk. All right. So hydrogen, as I have just said, there we go, is very important. And in particular, I'm going to talk about molecular hydrogen a little bit more because it is actually the fuel that makes stars, this phase of hydrogen gas specifically. So on the right here, we have a star forming region. And on the left is a little schematic of what this star forming region looks like, where basically star formation is a fight between gravity and between heat, actually, because heat is the orange arrows here. It's sort of making these molecules bounce all over the place, and it's preventing them from falling towards each other through gravity, which is the purple arrows here in my diagram. So eventually, over time, as these molecules lose their heat, gravity takes them and it starts pulling them towards each other and it condenses. And it's sort of a runaway effect where it continues to cool as it condenses. And it condenses and it cools and it condenses and it cools until you get a very, very dense molecular hydrogen cloud until it can like no longer support itself against gravity and it falls into a star and it ignites nuclear fusion. So that is the star formation process that's sort of key to our whole universe, key to how we got here today. But it's not something that's very easy to see directly. Because this molecular hydrogen is just two hydrogens, it's a very symmetric molecule, and that means it doesn't really emit light on its own, because you need like asymmetries to get to emitting light. And so we cheat. We don't look at the hydrogen directly when we're trying to study these molecular clouds. Instead, what we look at is tracer molecules. So molecules that, from empirical evidence, from just observing the universe, tend to fall into the same regions as the hydrogen molecules. And one of these molecules is CO, it's carbon monoxide. And so what happens with carbon monoxide is it forms in very similar conditions to the molecular hydrogen, and it exists in these molecular hydrogen clouds. And it is emitting light. It is not symmetric. And so when it rotates, it actually emits light at a very, very specific wavelength. And that means that it's really easy to identify it as carbon monoxide because we see light peaking at that wavelength. And the other thing about carbon monoxide is when it's inside a molecular cloud, the cloud is actually so dense that you can't see the carbon monoxide. You can only see the stuff on the outskirts of the cloud emitting this specific spectral line. And that means that because these clouds tend to be circular, there's a relationship between the size of the cloud and the the surface area of the cloud, the size of the cloud on the sky, and the mass of the cloud. And then because you're only seeing the outskirts of the cloud in this carbon monoxide spectral line, you can actually extrapolate from the amount of light you see in this carbon monoxide line to the total mass of the cloud. So it's very useful for studying star formation, is carbon monoxide. And that means that in order to study star formation, we need a carbon monoxide detector. And so that's what I'm going to be talking about today, is my specific experiment studies CO, carbon monoxide. It might be pretty fast, but I think let's do our second poll on checking our CO detectors. So I observe with this telescope every day. So I check my carbon monoxide detector every day. When was the last time you checked yours?
Well, I think I better pass on that question because I don't honestly, you know. It's, oh, it's going to be interesting to see what the answer is there.
Yeah, I'm curious.
So we'll wait another 30 seconds.
Perfect. Let people run it.
Okay, I'll share the results. So what do you think, Delaney?
Oh, there's a lot of numbers in there.
Yes.
Uh-oh. Yeah, this is your reminder to do that.
But I'm still amazed that there's 7 out of 46 who said this week. I'm really,
Yeah,
wow,
that's wild.
wow.
Good for you.
Yes.
All right. So I mentioned that COMAP is just a giant carbon monoxide detector. In practice, what that looks like when you're looking at a nearby galaxy is something like this. So we have the antenna galaxies merging here in visible light. This is sort of the big press image that everyone always looks at. It looks beautiful. But you can also look at it in what's this carbon monoxide emission, which is here in the red. And so you can see if you line up sort of this center region tends to be emitting in carbon monoxide. This center region tends to be emitting in carbon monoxide. And then along the spiral arms, there's also some carbon monoxide emission. And so this is sort of what I was saying earlier, where because stars form from these molecular clouds, where we see the carbon monoxide is where we see the molecular clouds, is where we see star formation. And so there's this lovely link that we're using to study galaxies. This is a nearby galaxy in an ideal case. In practice, it looks something more like this, what we see. So over here on the left, we have the actual imaging. You can see it's not really resolved at all. It's just a blob. And then on the right is what the spectral line looks like. This is intensity of light as a function of velocity, or as a function of wavelength, which we'll explain a little bit more later. And this is actually my undergrad research. So this is carbon monoxide in action. So that's CO, sort of the CO part of COMAP. Now we're getting into the map part. So mapping the universe through both time and space. What does that mean and how do we do it? So some of us may have seen this diagram of the history of the universe before or something similar to it. There's some things that we are pretty certain about the history of our universe. We know it's roughly 13.8 billion years old, plus or minus a few decimal points of a billion. It started with a big bang, and then there was a period of inflation, and then there was a long time where the universe was mostly just neutral hydrogen. It was pretty quiet for a while, and then eventually stars and galaxies started to condense out of that, and we start getting to our picture of the universe we see today, where there are many galaxies, and there's big voids of nothing in between them. But what I'm going to talk about today is how do we know that? This is like a timeline of the universe running back in time. How did we get here? And in order to explain that, we're going to start with this guy, Edwin Hubble. And so Hubble was one of the first people to notice that there were galaxies other than our own. He's very famous for that. The Hubble Space Telescope is named after him for that reason. But he also did some very critical work coming up with this diagram. This diagram, all the points on here are individual galaxies that Hubble measured. And on the x-axis, we have the distance to those galaxies, which is measured using a specific kind of star called a Cepheid variable, where there's a very predictable relationship between how often it pulses and how bright it is. And so you can use how often it pulses to extract how bright you think it should be, and then compare it to how bright it actually is to get the distance, because light fades as it travels. And so that's the distance to these galaxies. But then he also noticed that they were moving away from us. All but some of these very closest galaxies have what's a positive recession velocity, meaning that they are moving away from us. And moreover, the further away the galaxies are, the faster they are moving away from us. This is called the Hubble diagram, and it was the first discovery of something that's sort of key to modern astrophysics, which is the fact that the universe is expanding. All the time, constantly, the universe is just getting bigger. And this obviously was very early. We have much more sophisticated measurements of this now, but you can see we're now into megaparsecs, so billions of parsecs. This was millions, and we're still seeing this relationship. And it's a very tight relationship, where the further away something is, the faster away it is moving. And this is something that we're still working to understand. This gets into questions of dark matter and dark energy, which are, key to our understanding of the universe, key to cosmology. I'm not going to talk about that as much today. What I am instead going to talk about is how we can use this as a tool to study the universe. We're just sort of going to take this as fact and then see what we can do with it. And in order to use this as a tool, we need to use something called the Doppler shift. So people stood outside and had like an emergency vehicle go by them, and it sort of goes, whoo! Every time I explain that, I think I'm not going to do the sound, and then I have to do the sound. But this is a diagram of this. So sound is a wave, just like light is a wave. And if you are standing still and you are listening to something that is emitting sound waves that is moving away from you, what's happening is this wave has peaks and troughs. It has a defined wavelength. And as the thing is moving away from you, the peaks are getting spread out because they're being emitted further and further away from you. And this makes the sound seem to you who's standing still like it's at a lower pitch than it actually is, because you have a moving sound source. This is called the Doppler shift, and it applies to light just like it applies to sound, because light is also a wave. It's made of peaks and troughs. And so if you have something that's emitting light and moving away from you, it looks like it is redder than it actually is, because longer wavelengths of light appear redder. And so we actually call this redshift. Here's a little video of how it works in space. We're not zooming in on the Earth here. We're watching the universe expand. And this galaxy is not moving on its own. The universe is moving it away from us. And as it's doing that, it's stretching out the light emitted by the galaxy, where it goes from shorter wavelengths that look blue to longer wavelengths that look red. This is called cosmological redshift. We'll just call it redshift. And this is an important tool because, like I mentioned earlier, molecules and atoms, things like carbon monoxide, emit light at very specific wavelengths. So this is an example spectrum of a star. It could be a galaxy, it could be anything. For our purposes, it will be galaxies. And you can see that this bottom spectrum is what it should look like. from studies on Earth of the molecules we're looking at. We know exactly which wavelengths they emit at. And this top spectrum is what was actually observed. And there's a distance between them, and that is called redshift. So I'm going to show a few equations here. I promise they're just trying to get across the relationship between things. The actual math isn't that important. What's more important is that things behave predictably with respect to each other. So here, this Z quantity, this is quantifying the amount of redshift we see. And the way we do that is by comparing the observed wavelength of the light we see, the wavelength in this observed spectrum, to the emitted wavelength of the light we see, the wavelength we know it should be. And the whole point of this is that this is quantifiable. This is something we can assign a very specific number to. And then we can use our knowledge of the Doppler shift to relate this specific amount of redshift to the velocity at which something is moving away. And we can take that, and we have our relationship from Hubble between the velocity at which something is moving away and the distance due to the expansion of the universe. And so the faster something is moving, the more redshift we see, and then the more distant it is. And so by looking at the redshift of a spectral line, we can actually quantify how far away something is. And this is extremely useful. So when we are trying to study the universe, it's pretty easy to know where something is on the sky. The angular coordinates we know are not that hard to see because they're spread out to our eyes. But how far away something is, we need to call upon redshift to actually understand that, to map the universe truly in 3 dimensions. And so when we are looking at our telescope, things that are further away are more redshifted, and we can quantify exactly how far away they are. And so this distance coordinate we get from redshift, and then finally time also maps with distance. And this is a little more confusing, but basically light takes a finite time to travel like anything else. And so you know the speed of light, you know how far away it is, you can do the math and figure out when it was emitted. And so with this tool, with the simple fact that the universe is expanding, which is a huge mystery that we're trying to understand, but also critical to actually mapping out the universe, we can get all 3 dimensions and almost 4 dimensions to understanding how the universe evolves. So this is the mapping part of COMAP, is we are trying to do this on a very large scale. And hopefully sort of keep digging in on this graph and understand it better and better and better. So the particular thing that COMAP is mapping is carbon monoxide, like I said. And the reason for that is we have this relationship between how stars are formed and the amount of molecular gas that is in a galaxy. And we actually know pretty well how stars are formed, how fast they're formed throughout the history of the universe. You can see that around redshift of 2, which is just that Z quantity I was showing earlier, peaks, the star formation rate peaks. This corresponds to about 10 billion years ago when you do the math on expansion versus speed of light. But we actually are not really sure why that's happening. And so we want to go to the fuel for how stars are made to sort of break that down and hopefully understand that. And this is actually much less well constrained. So there are a couple of reasons for that I'll get into, but basically this is the same plot where we have redshift on the x-axis, and on the y-axis we have the amount of molecular gas in the universe, the amount of fuel for star formation. And these big boxes are they're what we call traditional galaxy surveys. They are doing this 3D mapping, but they are pinpointing individual galaxies, and they are actually not a great measurement of the total amount of molecular gas in the universe, because how should we do this? Because of that thing I was talking about earlier, when we were talking about James Webb. Actually, that was a great leading question, where we can only see the really bright stuff when we're looking really far away. This is actually even worse for something like carbon monoxide, which isn't that bright of a line on its own. And so these are sort of lower limits on the total amount of molecular gas in the universe. And I'm going to get into how we get these upper limits and how we get actual measurements in this next section, where I talk about line intensity mapping, which is sort of the other component to the map part of COMAP. So this is just a graphical illustration of this concept I was mentioning, where when you were doing a traditional galaxy survey, something like James Webb or DESI is a big one, SDSS, that sort of thing, when you're trying to map galaxies throughout the history of the universe, you're using this concept too, where you're exploiting redshift to see how far away things are. But you are also, you have to detect the actual galaxy. It needs to be bright enough for you to see. And that gets harder when galaxies get further away, and it gets harder when galaxies are fainter. So in this cartoon traditional galaxy survey, we're probably not going to see this galaxy. And there might be others further out that we're not seeing at all because they're too far away. And this is a problem when we're trying to get something like the total amount of molecular gas in the universe, because we think there are actually many of those faint galaxies and we want to be able to see them. So this is another of my schematics. This is a simulation based on actual data. We think sort of your like quintessential traditional carbon monoxide galaxy survey that's pinpointing things one by one would be able to see galaxies above some certain brightness. They'd be able to see something like this. But actually, we think that most of the universe is faint galaxies. So the actual number of galaxies out there looks a lot more like this, where the white ones are galaxies that the first survey didn't see. And so this is a huge problem if you're trying to understand how much of something there is in the universe. We use carbon monoxide, but it could be anything. And so the strategy for that is actually to take a blurry picture on purpose of the universe. So what we do is we deliberately have a telescope with a fairly poor resolution, and we look at the universe. We scan over a big region of the universe, looking at these galaxies that are here. And instead of pinpointing individual galaxies, our resolution is so poor that many individual galaxies fall into a single pixel. And this is on purpose because what we're trying to measure is the sum of the light from all of those individual galaxies, the total integrated emission, we call it. And this means that you get the light from these individual galaxies because you're not like rejecting any part of space where you don't see anything. And this means that you can do a measurement of how much light there is total of your molecular, of your spectral line, of your CO, or of any other spectral line you're trying to do. So we're mapping the universe in 3D using redshift. That concept also applies here. You just take pictures at different wavelengths and you see how much light there is at each wavelength, and you correspond that wavelength back to a distance or to a time. And so this is the concept of line intensity mapping. This is what I do. And I'm going to talk now about the specific telescope I use to do it. So COMAP sort of explains the why, the CO and the M. I'm going to get into the last two parts of the acronym here. So it was the CO Mapping Array Project. And I'm going to talk about the array that we use and sort of the overall project. So this is a picture from on top of the dish of our radio telescope, which we call the COMAP Pathfinder. This is what it looks like at night. It's located in the Owens Valley Radio Observatory, up in sort of central California near Death Valley. And there's lots of different radio projects from Caltech here. We're just one of them. You can see there's also all of these other dishes in this picture. And so COMAP is a radio telescope. Often when we think of radio waves, we think of the actual radio, and we sort of keep them separate from the light we can see in our minds. But they're the exact same thing. They're just part of the electromagnetic spectrum. which goes all the way from radio waves up to gamma rays. All of it is just a wave that is electricity and magnetism combined, and it has a specific wavelength. The only difference between the light we can see with our eyes and the light probably most of you are used to studying and radio waves is just that the wavelength is longer. And so in this graph here, we have sort of the typical size of the waves, the typical wavelength of the waves of these different parts of the electromagnetic spectrum, compared to like things that we might be more familiar with. And COMAP is actually about here. The wavelength of light that we're targeting for this CO transition, redshifted, is about a centimeter exactly. And so you'll notice this says microwave in this little diagram I have. That's just because astronomers are kind of lazy and we tend to group stuff together. And so basically anything below the infrared, we consider radio when we're talking about it. And so COMAP is falling right about here, but it's still light. It's just like visible light we see with our eyes. And so the COMAP telescope actually works a lot like sort of your traditional telescope. It just looks a little different. So exactly like an amateur telescope, we have our big primary mirror. In this case, it's white, but it's doing the same thing. It's reflecting light up towards the secondary mirror, which is here, and then down into our detectors. So in the case of an optical telescope, that would be either a camera or your eyes. But same thing here. And the primary mirror doesn't look like a mirror. It is white. You can actually walk around on it. Here's me doing just that. And that's totally fine because the wavelength of the light we're looking at is so long that like the little imperfections that mean that it doesn't reflect visible light are totally fine for these radio waves. So I can stomp on these mirrors and dent them a little bit and get dirt up there, and that's not a huge deal. It still reflects the light just as well because the wavelengths are so long. And so here is another picture of the COMAP telescope. Here's some of my collaboration. I'm not actually in there. This picture was taken before I joined. But what we're doing here is zooming in on this detector because it doesn't look like the cameras that people are probably used to seeing. This is what's inside. This is just a cover, the white thing. And inside of that are these 19 feeds, we call them. We call this a focal plane array because there's an array of these feeds at the focal plane where the light from the mirrors focus of our telescope. And this is the array part of COMAP. And this works just like an optical camera's detector array. So your CCD or your CMOS chip. This is the MIRI detector array from the James Webb Space Telescope. And basically, each of these individual feeds acts like a pixel over here. And so we only have 19 of them, whereas there's about 1 million over here. This is because, again, the wavelength of the light is so long. That's helpful for us when we're reflecting it off our white primary mirror. We don't need to care about it being super reflective to optical light, super shiny. But it's less helpful here, where the light, even though it's been focused a lot by the telescope optics, it is still really big. And so these feeds have to be quite large. This is probably the size of my arm, the height of these, to actually bring the light into the electronics. And so we can only get 19 of them, where you could get about 1 million into the James Webb optics. Another way of looking at this is resolution. So this is, I think, my last equation. But what this shows is the resolution of your telescope as an angle. So the smaller the better, because that means that you can see tinier things. And it scales with the wavelength of the light you're looking at and the size of your telescope. So our telescope is 10.4 meters. It's actually about the same size as the James Webb primary mirror, but we are looking at a much longer wavelength of light. We're looking at 1 centimeter wavelength, where James Webb is looking at about a micron. So that's like 10,000 is the factor between the two. And that means that this is about the same. This is a constant. This is about 10,000 times worse. So our resolution here is about 10,000 times worse. And so we have 10,000 times worse resolution. We've got these giant feeds. We only have 19 of them. All of that is actually fine. And that is for the reason I was explaining earlier, where when you are doing line intensity mapping, you actually want a poor resolution telescope on purpose. It sort of works out. The light wants to be poorer resolution because it's such a long wavelength. And so our telescope optics can't produce a very good resolution, but that's fine because that's the application we want it for. And so I've always thought this was like a really clever sort of instrument design. So in practice, what COMAP is doing to map the universe, we're not mapping the whole sky. That would take forever. Instead, what we are doing is we are focusing on 3 different fields in the sky. 2 of them are shown compared to some constellations here. One of them is sort of over this way. And each of these are about a degree in size. They're sort of thumb size if you put your thumb like all the way at arm's length. They're pretty small on sky, but they are enormous in practice because they are so far away. And what we do is when we are looking at the sky in 2D, we take our big telescope and we can't, because we have only 19 pixels, we can't really take like a traditional picture where we just keep it still and we take a snapshot and it does the spatial axes for us, like something with a lot of pixels can do. Instead, we have to scan the sky. And so we take our telescope and we focus on one corner of our field, and then we scan it across, and then we go down and do it again. And then we sort of just keep doing that until we've covered our whole field. And with the poor resolution of COMAP, that looks something more like this, is what ideally we would see. But this is a simulation, and unfortunately, we also have to contend with instrumental noise, just like an optical telescope does, where you have your sort of your dark energy, dark current, shot noise, all of that affecting your image. This is just something I pulled showing a very noisy image and a less noisy image. The exact same thing happens to radio telescopes for slightly different reasons. It's actually temperature fluctuations in the electronics that cause the noise to happen, but that still means that our images are very noisy. And like with optical telescopes, where when you're trying to get a better image, what you do is you either stare for longer, you integrate for longer, or you stack images together in order to get a longer total integration time. What we have to do is we have to stare longer at our patch of the sky. So this is more what it looks like right now, what we are looking at, our fields, where it's mostly just noise up there. This is actually what our state-of-the-art data for our telescopes looks like right now. These are our 3 fields. And so pretty much all we can see right now is noise. Okay, so let's regroup and do the last poll, I think, because I'm going to talk for a few minutes after that about specifically what I do with the COMAP data, if all we're seeing so far is noise. But before that, have you ever seen a radio telescope in person? I'd also be very interested.
Yeah, it would
Sorry,
be very interesting, and maybe we should have added how many have you actually seen? That's what
yeah,
would I would like to know that. Maybe you can put it in the chat if you've seen more than one. How many have you seen, and where have you seen them? Just put it in the chat for interest.
yeah. Also very curious if anyone has ever been to Ogro, been to the Owens Valley Radio
Yeah,
Observatory.
Parks
They do
Australia, of
tours.
course. John is saying Parks
Yeah.
Australia. No wonder. Yes. Angela is saying, okay, one in Jodrell Bank. I have not been there. That's interesting. Yeah, Siding
Nice.
Spring. Yes, exactly, Max. That's where we went. Yes, that's right. Franz Josef saying,
Oh,
Alma. Yes, very large in New Mexico. Ian saying Stanford. Oh, one homemade. Listen to that.
That's pretty cool.
Ah, Martin saying, unfortunately, never seen one before. Oh, Haystack Observatory in West Massachusetts. I don't know about that one. Do you know that
Me
one?
neither. No,
Interesting.
that's cool.
Brian saying Mulford, Cambridge. Yes. Interesting. Wow. Okay, let me just share the results. This is really interesting.
Ethelsberg, nice. I did
Yes.
see one who has seen Owens Valley, which is pretty cool.
Oh, yes, near
Oh, more than
Stockholm,
half.
Sweden. Yes, that's right. Effelsberg, of course. I've been there. Yeah, I grew up in that area in Bonn. So I've seen that one. Yes, interesting. Yes. Um, oh, this is very interesting. I didn't know there was an Alma Nova radio telescope in Stockholm. Must have missed that, Peter. I should have known that. Interesting. Wow, very good. Oh, and Pew in India. That's interesting. Nakul is saying. Okay. Well, so what do you think of the results?
That is actually far more than I would have thought.
Okay.
That more than half of people have seen a radio telescope. That's really cool.
Yeah. Yes. Oh,
Yeah, they do come in many, many different flavors is the other thing. A lot of them look even weirder than mine, which has like a really obvious dish.
interesting. Interesting. Yes. And thanks, Peter, for the link. Okay, so please continue.
All right. So I'm just going to talk for a little bit more about what actually goes on scientifically with the COMAP data. So we've got these three fields. We don't see any of the carbon monoxide emission in them that we're actually looking for. So what do I do day to day? How do I work with these sort of non-results? And the answer to that at first is just simulations. So that's a huge part of preparing for especially a like custom designed instrument like this, something where we have a very specific spectral line that we're targeting using a very specific method. We sort of need to give our best guess as to what we think it will look like based on other evidence. And so I do a lot of simulating what I think the data might look like once we finally get it in order to sort of plan for what to do when we actually do see it and to sort of help us believe if we do see something in the future that it is actually what we're looking for. And so I work with simulations that don't look quite as cool as the big video I showed earlier, but I think they're still pretty neat. What they are is it's sort of a big map of a simulated universe with a simulated distribution of galaxies in it, and then some fraction of those galaxies are emitting CO, and that sort of corresponds to the size of the galaxy and whether there are other galaxies nearby. And then what takes a lot of work is actually coming up with what we think the instrument would see given that distribution of galaxies. And so this is a simulated distribution of galaxies on the left. On the right is actually a simulation of what COMAP might see if it stared at that distribution of galaxies for long enough. And so this really drives all of the other work that we're doing in order to sort of tease out statistics from the data that we have. And so one of those statistics that we use a lot is called a power spectrum, which you might have heard of or worked with if you are familiar with the cosmic microwave background. So basically, what this is we have spatial scale on the x-axis. So we are measuring something as a function of the size of the something. And the something we are measuring is how many fluctuations there are at that spatial scale. So if there was a bigger peak over here, that would be when the GIF loops. Most of the universe is like really large scale. There's sort of huge objects out there, and the correlations between them exist on really big scales. But if peak is more over here, most of the universe is at a smaller scale. And this is sort of just a way of understanding the size of characteristic objects in the universe, understanding the size of like gravitational relationships between things in the universe. And so this is a very powerful tool to understand our noise maps and hopefully our signal maps, because this sort of map will have characteristic spatial fluctuations that we can then use to understand the characteristic distribution of the galaxies that the map is made from. So that's it in simulations, but in practice, you actually get, hopefully, some measurements of that. And then this is what our actual power spectrum looks like right now. We just did a data release a few weeks ago. So same thing here. You can totally ignore the labels here. This is just characteristic spatial scale, and then amount of fluctuations we see at that characteristic spatial scale. And these green and magenta lines are sort of predictions for what we should see with these simulations I was talking about earlier. And then these black lines are our upper limits on what we do see. So we don't see any fluctuations so far, but it's actually still very constraining, the fact that we don't see fluctuations, because we know the size of the fluctuations we should be sensitive to. So these are constraints on what the universe looks like based on the fact that we don't see anything, which is still interesting, even though we haven't actually seen what we were looking for. What you want to take away from this is that these black lines are getting kind of close to the green and the magenta line. And we are not done observing. Hopefully we will, in the next few years, actually get sensitive enough to see the green and the magenta line, or the magenta line, and see which one is right. The other thing is that we get a measurement of the total amount of molecular gas in the universe. That was sort of how I framed this at first. And this is probably the first thing we'll be able to measure, is from this power spectrum or from other statistical analyses, just a bald measurement of how much CO, and therefore how much molecular gas there is at a certain point in the history of the universe. And so this is sort of what I posed earlier in the talk as our sort of lack of understanding of the history of the universe. We've got these lower limits from traditional galaxies. These are upper limits from actually other surveys using the same technique. And this is the exact same plot. Sorry, the colors are different, but with our latest limits put on it. And so you can see that we are still an upper limit, but we are actually getting kind of close to where the lower limits are. And sort of as we get down, we'll sort of pinch the actual number between the two limits, and we'll get a good constraint on what actually the number is, even if we don't see anything. The fact that we are at this point is still pretty interesting. And so this is just another sort of picture. All it is just the y-axis of this plot, the total amount of molecular gas in the universe, compared for different experiments that have looked for it and different models. So there's a lot going on here. I'm going to get you to focus just on these colorful lines up top first. These are the traditional galaxy surveys. They're the boxes here. And you can see that they have sort of lower measurements of this total amount of molecular gas in the universe. This is the lower limits again. This black line is COMAP's latest constraint on the total amount of molecular gas in the universe. And this red thing is where from our simulations we think it's going to be. So we are very close. The way to get to actually measuring that is just to stare longer and beat down that noise, the exact way you would do with an optical telescope trying to get rid of the grain in your image. And so that's basically our plans for the future. Is we have this telescope, it's working great. We have a good picture of what we think is going to be there, and the plan is just to keep staring until hopefully we see something. So I'm going to leave it there. I'm sure there will be questions. Hopefully it's okay. I'm also going to plug, I don't really have my own social media, but I'm very active with Caltech's astronomy outreach program. And so this website has our events. We also do live streams. And there are many YouTube videos as well, including one of me talking about a specific type of galaxy on our YouTube, if anyone is interested in that.
Thank you so much, Delaney. Do you mind just stop sharing so we can see you better? So thank you so much for that very inspiring and intriguing talk. I must say, very different to what we've ever heard, at least from my perspective. Really interesting. So I'll just start with one or two more clarifying questions, then I'll hand it. So don't forget to put your questions in there, please, on the Q&A section. So it's very interesting. So obviously, what we saw of the 3D maps so far, what you've shown are simulations, right? Can you just confirm that that's all simulations that you've shown so far,
Yeah.
right? Exactly. And my understanding is you've got one dedicated radio telescope at Caltech, though doing nothing else but trying to solve this particular problem, but the sensitivity isn't quite there yet. Is that correct? So you're not quite there. That's what I gather from and you said you're still a few years away. Can you give us a little bit more information what
Yeah.
that means?
So the thing is, the issue with CO is it's extremely exciting and like scientifically interesting to study this line specifically, but it is an extremely faint line.
Yes.
And so we have this telescope. It's the biggest one we could get our hands on. We put the best electronics we could get our hands on onto it. And it is dedicated to just scanning the sky for CO in our three fields. It's been going since 2019, sort of on and off. We've had some electrical problems, but it's sort of scanning pretty continuously now. And based on our predictions, we thought it would take 5 years of continuous observing
Right.
to actually see the signal. And we're sort of 3 years into that 5 years
Okay. Okay.
in
Sorry.
terms of actual time on sky. So hopefully within the next 2 years, we will be able to see something.
And just a hypothetical question. Let's assume you could use other radio telescopes too. You could put your instruments on it. Would a coupling of radio telescopes actually help you get the sensitivity just like that? Would it work if you had that possibility?
So a lot of radio telescopes use a trick called interferometry, which I think you're thinking of,
Yes, that's right.
uh, which is nice because it gets more dishes on the sky, but it actually, what it does is usually when you're using an interferometer, you're chasing spatial resolution.
Hmm.
And so when you
I see.
combine the data from your two dishes using
Right.
interferometry,
Right.
you zoom in on the sky a lot more. And that's a very useful trick because, like I said,
Mhm.
these sort of just inherent facts of radio waves mean that it's hard to get that spatial resolution. And so for a lot of applications, that's a good thing. But for us, it's actually not
Mhm.
because we want that intentionally poor spatial resolution.
Mhm.
What we could do is we could have two dishes just totally independently staring at the same fields on the sky and sort of each scanning on their own. And that would essentially be the same thing as observing for twice as long with our one telescope. So it would
Right.
give us a gain in sensitivity. And it is something that we are proposing for
I
more
see.
funding to do. But it's not quite as big a gain as like bringing an interferometer into the mix.
But the strength is really that you have one dedicated radio telescope that you can really, so time is not the problem here, right? That usual
Yeah,
human
exactly.
return, right? So
Yeah.
interesting. Thank you. Very, very interesting. Okay, so I'm going to jump over now to the audience. Max Whitby, the author of The Visible Universe, a beautiful book, by the way, a really beautiful book. I can recommend it. He asks, and that's a good question. How do you actually focus a radio telescope? Do you have V curves similar to optical telescopes? How do you do it?
It's pretty similar. So it's not quite something like with an optical telescope. My understanding is you have to do it slightly more often because it's so precise. With a radio telescope, it's like not as precise, and
Okay.
so
Okay.
because the wavelengths are longer,
Mhm.
it's not quite as tiny an area you're pinpointing with your focus, but it's sort of a very similar strategy.
And just to throw a question on that, you focus it every few hours, once a day, once a week? How does it actually work?
I think it's once every couple of months. I think we should do it a little more
Really?
often, but
Okay,
it's not very often at all. Yeah.
so the
It's sort
answer
of
is Max, it's very different. That's my understanding.
we set it and
Interesting.
forget it.
Interesting. Okay, and Peter's asking, do you publish COMAC data to Worldwide Telescope? Do you know that?
We don't publish it to Worldwide Telescope. We just because it's sort of currently it just looks like noise, and so there's a lot of processing that we have to do even to get our power spectra, and so
Right.
it's not really something that would be
Okay.
interesting to most people, I think. We do have plans to publish it on a NASA website called Lambda, which is more dedicated to cosmological instruments, but we don't have it up there yet. Hopefully, it will be soon.
Okay, and then Peter gives a link there. Thank you very much. That's a link to the Worldwide Telescope. That's what he was doing. Martin is asking, the more far away the galaxies and gas clouds are, the less amount of CO would be available because the amount of these metals, carbon and oxygen, reduce in the more younger universe, right? Are these weak and possible non-detections compensated by other markers instead of CO? Wow, that's quite a
Yeah,
question.
that's a really insightful question.
Hmm.
So yes, but not on the distances that COMAP is concerned with. I think is the short answer. The longer answer for people who are maybe less familiar is that things that astronomers call metals, which is anything heavier than hydrogen and helium, those have to be made in stars.
Mhm.
That's the only place they're made. They weren't produced in any significant quantities at all in the Big Bang. And so you need at least one cycle of stars forming out of hydrogen and helium and then living through their lives and exploding to enrich the universe with these metals. And so carbon and oxygen are metals in terms of the like astronomer definition. And so they only come from stars that have lived and died. And so we need that to have happened before we can use them to observe molecular gas. And so early on in the universe, we can't observe molecular gas through this strategy. But by the time we get to where I'm looking, which is about 10 billion years ago, it's about redshift of 3, there should be enough of it in the universe, enough carbon and oxygen, that it won't be a huge concern. Um, there's still like the ratio between the amount of CO molecules and the amount of molecular gas does slightly matter for calculating the amount of molecular gas from the amount of CO emission you see, but not as much as you would think because of that thing I was talking about where it's only the outskirts that affect how much you see. So if you have less CO, all that happens is the region of the outskirts that you're seeing gets deeper into the cloud and it sort of compensates for itself. But line intensity mapping as a strategy is also used to observe the very early universe. It's a really good thing for doing that. And so we do use other tracers for doing that. One of the big ones is actually 21 centimeter
Mhm.
um, experiments, which people might have heard of. This is just neutral hydrogen has a very faint line that it emits. And so it would be tracing a different kind of gas.
Thank you. Very good answer. Nakul is asking, what are the tools and information you use for simulating the galaxies and redshifts?
Yeah, so again, very technical. Basically, what we have is we have a bunch of dark matter only simulations. So all of this stuff that I've been talking about, all this hydrogen and carbon monoxide, this is what we call baryonic matter. And it exists sort of inside of big halos of dark matter. And so what we do is we start with just a bunch of basically randomly scattered dark matter halos. I think we use some information from things like the cosmic microwave background to distribute them a little more reasonably. And then we just let that population of halos evolve using gravity through time. And so we get from this dark matter only simulation, we get a fairly realistic picture of where the dark matter should be. And then we go in and we say, okay, we know from observing galaxies that things with this dark matter mass probably have this mass of hydrogen and this luminosity of CO. And we go
Mhm.
in and we paint those luminosities onto the dark matter halos.
Right. That's quite a complicated way. So you go very detailed. Well, good question. And if you share a cool experience, whatever that means. So,
A cool experience. I think uh, that's a good question. I've been up to see COMAP, the telescope,
mhm,
3 times now, and it's always really cool. Most recently, we put like a weather monitor on it that I helped to design and build, and that was really neat because I had not done that sort of instrumentation work beforehand. It's gorgeous up in the Owens Valley is the other thing. There's like 10,000 feet of elevation gain of relief with the Sierra Nevada mountains, and they were
beautiful.
snowy when I was up there. It was beautiful.
Thank you. That's a great answer. Martin's asking more another direction now. So, would the data from the Dark Energy Survey instrument DES be useful for what you are doing?
Absolutely. And so that's actually what I've been talking about is mostly COMAP in general, the whole project, which there's about 30 people working on COMAP. There's far more than just me. My specific thesis is actually on taking data from traditional galaxy surveys like DESI, the Dark Energy Survey instrument, and combining that with the COMAP data to hopefully see something before COMAP sees it on its own. Because you have information about where the galaxies are in space, you can sort of extrapolate to where you think most of the CO emission will be and use that. And so DESI is one of the other experiments that I've been using. They don't have a ton of data in the COMAP fields yet, so it's just an issue of pure and simple lining up in space between their data and ours. But other surveys like EBOS from SESS, the Sloan Digital Sky Survey, um, do line up well with the COMAP fields. And there's also a survey called HETEX, which is the Hobby Eberly Telescope Dark Energy Experiment.
Mhm.
They're studying mostly neutral hydrogen in galaxies at about the same distance as we're studying, so about the same redshift as we're studying, and so they line up very nicely with us.
Interesting. Thank you. And finally, Richard, regarding noise, do you share data and screening techniques with LIGO? That's interesting. So, hmm,
Yeah, that is an interesting question. So in terms of data, not really, just because we're looking so much further away than what LIGO is sensitive to right now. Anything from the region of space we're looking at would be sort of the background for LIGO. They probably wouldn't see the individual objects we're looking at. There is sort of a broad yes, though, in terms of just like noise sort of behaves the same way
mhm.
no matter what you're doing with your data. And so absolutely we share like data reduction techniques with LIGO. They also look at things as a function of frequency a lot.
Right,
They
right.
sort of tend to make these 3D maps that we're doing. And so that is a nice overlap between them.
Interesting. Yes. And finally, Ian says, say hello to Chummels.
I will.
Very good. That brings us to the end of this wonderful webinar. Thank you so much, Delaney, again for this really incredible talk that you gave, and especially we wish you lots of good luck, and hopefully you'll get some useful experimental data soon that can confirm whatever your simulations have predicted. Hopefully not a complete surprise.
Yeah,
And
that would be pretty cool though if it
yeah,
was
it would be.
totally
Yeah,
unpredictable.
well, in either way, it's going to be cool. So good luck with it, and thank you everyone for your participation, your support here, and have a wonderful weekend. And we'll see you soon again. There'll be more webinars coming up. So all the best to all of you, and thank you again, Delaney. Thank you.
Okay,
Okay.
thank you so much for having me.